there are quite a few actual scenarios wherein dipoles will be exposed to electrical field. So analyzing, understanding, and making use of it is our goal. So we'll start with the most simplest form, wherein we have dipole being kept in uniform electrical field. So the word uniform over here, what does it mean? So uniform electrical field, first thing is let's talk about electrical field. So field, word field deals with a space. Electrical field will deal with electrical charges or charges experiencing force in this space. So what is uniform about this? The thing that is uniform about this is if I keep a charge over here or over here, over here or here, a certain charge, same charge, all of this will experience the same force. Even though they are in different position, they'll expose or experience, not expose, experience the same amount of force. Say it's experiencing a force of 10 Newton over here. It would be so 10 here and it will be 10 over here, or it will be 10 over here as well. So basically it will be 10 pretty much everywhere. And that is your uniform about your uniform electrical field. Thus both charges regardless of their position will experience the same amount of force. But the orientation of the dipole, it matters. The orientation of the dipole results in torque, something to do with rotation. So basically the dipole rotates. Why does it rotate? We are going to see the math. So overview is that we are going to consider electrical field which is uniform. We'll consider dipole. We will draw the free body diagram for this set of forces. We'll resolve it. And we'll see that translation wise, that is movement wise, is only rotational. There's no translation. There's no linear movement. It won't go left and right. On an average, the center of the entire thing will remain the same, basically. And we'll see when is the maximum rotation maximum, when it's stable, when it's unstable. So what position of the dipole? Will it be stable? Will it not move? In which scenario will it move? And which scenario it will have the maximum rotational strength. So that's how we will end the derivation. So your official derivation starts over here. As mentioned, we have uniform electrical field. We have negative charge and positive charge. And the distance between them is 2a. This is the center. So this center will not move at all. It won't go left and right. Next, this will be the direction of your dipole moment. It's pretty important because all the things that we talk about will be with respect to dipole moment. Now, common sense tells that this charge minus q, forget about everything else, will experience a force to the left with F minus q as its force. While this positive charge will experience a push away in this direction. Agree? Simple. Now, let's resolve this. In what direction will we resolve? With respect to P. That is your dipole moment. So free body diagram of say negative Q. Let's start with that. So this is the force that that's it experiencing. We need to consider an angle to discuss all of this further. So the dipole moment and the electrical field forms an angle of actually minus theta and all of that, but we'll just call it as theta as of now. So this also will be theta, alternative interior angles and all of that here. Same angle. Same angle. Now, let's resolve. That's your cos component. That's your sine component. Agree? So if this is your force on negative Q, this would be cos theta and this will be sine theta. Is this correct or have I done something wrong? Can you pause and check? Yep, I've not done anything wrong over there. Again, I can do mistakes and you guys have to catch it. So positive charge, it's experiencing a force to the right as per my diagram. That will be your theta. Again, alternative interior angle. And your force will be resolved perpendicular to that and in that direction. So we have this to be, this is your sine theta and that's your cos theta. Right? So let me put it in this diagram. So that's your sine, that's your cos, this is your cos, and that's your sine. Before I proceed, what do you think happens to this force? What is the net force between each of this component? Please think of it. Think of every question that I ask. You can pause, that's the advantage. Make use of the technology. Have that sense to make use of the situation so that it helps you to grow. Okay. So what's going to happen? Well, if you think about it, f minus q cos theta, so the cos theta component, they're opposite, so they will cancel each other out. While your sine theta component will, well, they're also opposite, but they're not acting on the same line. While your cos theta component are acting on the same line. Agree? So let me conclude over here. So from the figures, we can conclude the cos theta components are equal and opposite, or let me put it this way. This is more, much more easier. Will cancel each other, right? Reason being, they are opposite in direction, first thing, and they're acting on the same line, and acting, well, are on same line. While your sine theta components are opposite but form a couple. Simple reason being, yes, they are on the same, acting on the same line per se, but that line is perpendicular, right? So this is here, right? Sine theta, if I think about this component over here and over here, they form a couple. With respect to this line, they are perpendicular, while cos theta are on the same line but in opposite direction, pointing in the same opposite direction but also on the same line. Agree? So we have force couple where the force component is f sine theta. Reason being, I'm calling fq magnitude wise, which is equal to F minus Q. I'm calling it as F. Next, in torque, it's important for us to see the perpendicular distance. What is the perpendicular distance between the sine components? What is the perpendicular distance? Here and here. The perpendicular distance is 2a. Okay, guys. So, perpendicular distance between what? Between the couple. Is 2a. Therefore, the torque is equal to 2a F sine theta. Agree? Now, the force in terms of electrical field is EQ. So, we have torque is equal to 2a EQ sine theta. But your moment is nothing but 2aq. I'm just substituting, trying to express final expression in terms of course, moment. So, EP sine theta. But torque is a vector quantity, remember? So, finally, I can express it as a cross product between dipole moment and the uniform electrical field strength, E. Right? So, that's your expression. So, a dipole in a uniform electrical field will experience a torque. Now, of course, we need to study this in detail. What if I have theta to be equal to 0 degree? So basically a case of parallel. What does this look like in terms of diagram? So if say this is your electrical field, so that's your negative charge. That's your, sorry, this is your negative charge because dipole moment moves from negative to positive, right? And that's your positive charge. So dipole moment will be in this direction. So in this case, theta is 0. So what will happen? Think of it being displaced a bit over here or there. Right? What happens? It will snap back. So this will make it a stable equilibrium. Agree? So imagine if I displace it a bit. So negative is getting pulled to the left while the positive is getting pulled to the right. So when you resolve the force, what will happen? We have a rotational strength force which will put it back to the original position. So whenever something puts back to the original position, such scenario is where we see stable equilibrium. Right? Now, what happens for theta is equal to 180 degree? That is anti-parallel. This is known as a case of anti-parallel. What do you think happens? So if this is the electrical field, say this is your positive charge, or let me do it with this color itself. That's your positive charge and that's your negative charge. So this is your anti-parallel. Reason being, your dipole moment is in this direction while the electrical field is in that direction. What will happen over here? So we have charge, say, displaced in this manner. So what will happen? So positive charge will be getting pushed to the right, negative will be getting pushed to the left. So they will rotate in this way. That is away from their present status. Here they will rotate in this way towards their present status. This is away from present status. So this is nothing but a case of unstable equilibrium. Again, you guys need to be clear with the definitions of what is equilibrium, stable and unstable equilibrium. Now, what if we have theta to be 90 degree? As per the formula, this would be EP sine of 90. So this is a case of 1, where sine 90 is 1. So torque is maximum. It's a case of torque being maximum. Okay, so these are all the different cases that a dipole, of course, there are many infinite possibilities, but these are the cases that we need to understand. Finally, now we can define dipole moment with the help of torque. So dipole moment has to do with how strong the dipoles are. If I make the torque, if I make the dipole to be 1, electrical field to be 1, and if they're kept at 90 degree, so this is electrical field strength is equal to 1 Newton per coulomb, and your charge is 1 coulomb. Oh, sorry. This is your electrical field and this is your dipole moment. Agree? So this is your dipole moment. So the torque will be, this will result in torque to be equal to 1. Is it not? If the torque is 1 in the presence of an electrical field which is of 1 Newton per coulomb everywhere, and the angle and the orientation of the dipole is 90 degree, right? We end up with this torque. Then the dipole moment is said to be 1. Torque acting on a electrical dipole placed perpendicular to a uniform electrical field of unit strength. So if the torque is 1, then the dipole moment would be so. Or let me put it this way actually. As per the definition, I'm actually telling it wrong. Torque EP sine theta. If I substitute E is equal to 1 Newton per coulomb, sine theta is 1, that is angle is 90 degree. From this I can tell torque is equal to your dipole moment, right? Because everything else will be 1. So the dipole moment will be equal to torque, or the torque acting on a dipole, electrical dipole, placed perpendicular, the direction is also done, to a uniform electrical field of unit strength. That is nothing but your dipole moment. That will be equal to your, the torque will be equal to your, in this case, torque is equal to your dipole moment. Actually, the statement is wrong. I mean, incomplete, more than wrong. This is incomplete. Okay, guys, again, what I'm trying to show here is you need not remember formulas or derivation. Formulas you have to. You need not remember definition, but you need to know how to derive. The minimum that you need to have is the formula in head, but the best way to do this is knowing the derivation. Everywhere and anywhere, wherever you see formulas, you need to know the derivation. Okay, guys. Now, this is the heading. And this is where your derivation starts. This is where the derivation ends. If they ask particular set of scenarios, you guys can talk about this. If not, you need not. This is your end of derivation.